Well, hello there! I hope you're having an amazing day and that you're feeling excited and ready to learn and extend your knowledge and your sight about memory and memory allocation and learn quite a few new terms that are being used and thrown around when talking about memory. So, are you ready? 3, 2, 1, go! Okay, the first term that we need to understand is going to be type layout. Okay, so type layout is defined by 3 parameters. The first one is size, the second one is alignment, and the third one is relative offset of the fields. Just a quick question. Are you aware of the fact that we have no idea what any of those terms actually mean? Of course, do not worry. I'm going to talk about all of these terms one by one, and by the end of this video, you'll know completely what each of these terms means. Okay, let's start from alignment. So basically, alignment of a value defines where that value can be stored in our memory. So basically, what are the valid addresses where we can store the value we are currently working with? And our compiler needs to figure that out. Excuse me, just a question. Aren't we just stacking values one on top of the other? I mean, why would we do anything else? We are wasting our memory that way. Nope, that's not how things work in reality. In some perfect theoretical world, stacking values one on top of the other would be possible, because that is the most memory efficient way to store them. But we are basically limited by quite a few things that are making us a lot of problems when trying to do that. So, in reality, that is not how it works. Okay, let's try explaining alignment using an example. So, let's start from the case where our alignment is going to be 2. So, basically, this means that our values are going to be stored only on even memory locations. So, you cannot save any value to our memory that is being located on an odd memory location. On the other hand, if we were using alignment of 1, we can basically use every single byte in memory locations. So we could use every single memory location. We do not have any limits. And yeah, you guessed it, 1 is the least number that we can use as an alignment, because you cannot go lower than a single byte of memory. And that is basically the reason why our Boolean data type, which we can basically store in a single bit of memory, we use a whole byte of memory to represent it, because we know that there is no way for us to access any memory location that is smaller than 1 byte. So 1 byte is the least amount of memory that we can work with, basically. And yeah, one more thing. You should have in mind that alignment can be any number that is a power of number 2. So basically 1, 2, 4, 8, 16, 32, whatever. But you should have in mind it's just a power of 2. It cannot be any like 3 or 7 or whatever number. It has to be a power of 2. So 1 is also a power of 2. It is 2 to the power of 0, if you remember. So just a heads up there. Okay, there are quite a few limiting factors that prevent us from being able to store values as you would like to store them, and in a most memory saving way also. So we have quite a few limiting factors here, but to name a few, the first one is our hardware, because we have to comply with the limitations that are provided to us by the physical world, because we might be working with ones and zeros and with like code and stuff like that, but our computer is basically a set of many trillions of transistors which are working together, and actually they comply with the physical laws that are being present on this planet. So we have to be aware of that, and because of that fact we are limited. And also, we have another limitation which comes out of the fact that pointers cannot point to bits in memory. They point only and only to bytes in memory. So our memory cannot be accessed one bit at a time. You cannot point to a third bit in some byte of memory. You can only point to that byte itself, and our pointer is going to point to the first bit inside of that byte, nothing else. And also, have in mind that our CPU does not access one byte at a time in memory. It accesses more than one. Our CPU basically uses its word size, which is 64 or 32 bits long, and then it picks up that amount of memory at a time. Of course, there are certain algorithms which allow our CPU to be working with memory chunks that are smaller than the word size, but that requires more time for our CPU, and also it increases the complexity of hardware and software that is being used to actually do that. So yeah, it's not a very good idea to do it, and that is why we are basically not being able to stack values one on top of the other and have no offsets within. Well, I hope that this brief explanation made things a bit more clearer about how our CPU works with memory. I think that now everything should start popping in its place in your head, and you should start having a better understanding how things work under the hood. And yeah, one more thing that I wanted to tell you is the fact that you can actually check in your Rust code what is the alignment of any value. We have a dedicated method for doing that. It is called align of val, and it looks exactly like this. And the second parameter that we need to cover right now might sound a bit more intuitive than the first one, but its name can actually be misleading. I'm talking about the size property. So basically, size defines the offset between two consecutive values that are being stored in memory. So not the actual size of the value that we are talking about and trying to store in memory. So basically, after we store this value of ours, it takes up some amount of bytes and defines how many empty bytes are going to be left besides that value before we can put another value next to it. So basically it's just an empty memory location. And when it comes to potential values that our size can have, you have to be aware that it can only come in multiples of the alignment. But it can also be zero, because it's completely valid not to have any offsets. Yeah, but also, 0 is a multiple of any number, because any number multiplied by 0 is 0, so that still complies with the rule I just stated. Okay, now that we understand what those two parameters mean, it's time to talk about a very significant topic in Rust. I'm talking about sized trait. So I'm aware that we still did not talk about traits, and I will cover this topic that we are talking about right now in its own separate video in future, but right now you have to be aware of the existence of this trait because it's very important. It's going to basically make a lot of troubles for you if you do not have at least basic understanding of it. So, when we know the alignment and size of our value in compile time of our program, that means that that data type that this value is of can inherit from sized trait. So when we say that some data type that we have created inherits from sized trait, that basically means that our compiler can figure out during compile time, so before we need to run our code, what is the alignment and size of each value within that data type. So basically, alignment and size are very advanced concepts in Rust, and basically any programming language, because they're talking about very low level stuff, and for most of people, they're never going to actually need to work with these parameters like directly. They should just be aware of their existence, and that's basically it. But of course, unless you're working with some very low-level stuff, you're working with embedded development, you're working maybe on writing an operating system or something like that. But in most cases, you do not have to worry about them. But when it comes to sized trait, you should definitely be aware of it, because you are going to be stumbling upon it many times for sure. So as an alternative to our sized data, so basically the type that inherits from sized trait, we have an alternative which is dynamically sized type. So basically, when our compiler cannot figure out the size and alignment of our value within compile time, that means that that value is dynamically sized data. So that means that our compiler cannot figure it out during compile time, but it can figure it out during runtime. And Rust compiler is going to throw errors at you because it does not know if it is supposed not to know the size of that data or it is not. So you have a special keyword that is supposed to tell our compiler that we know what we are doing here and we want it to trust us, because it will get the data it needs, but only it will get it at runtime. And the keyword I'm talking about is dyne, but we'll talk about it in future. I just wanted to share some broader view about the whole situation and what is the alternative for data types when it comes to being sized or not. And we're basically done here.
Hey, do you consider us senile? You promised to explain what type layouts are and you just mentioned parameters that define them. You did not define the term itself.
Ha, but of course, apparently I'm the one who's senile, not you guys. Okay, now that we're familiar with the concepts of alignment and size, we can extend that and actually define what layout is. And the definition is very simple. Layout tells our compiler how big the alignment and size are going to be. Basically, it is going to standardize alignment and size across our platform, across our project. So we do not have to worry about it all the time and define it on every data type and then have different layouts throughout our project. That would be horror, that would be terrible. Because, for example, C and C++ use completely different layout for memory. And that is why when we try to collaborate and make some external calls to C or C++ methods that are being externally included in a Rust code, we would get memory corruption for sure. That would happen 100% of the time, because C and C++ are storing variables in memory in a whole different way when compared to the way that Rust stores them. And when we are working with Rust and we are calling some C external functions, that means that we will have two different memory layouts. And that can only lead to one thing: memory corruption. That is why it is essential to tell our compiler which memory layout it should be using. And to specify that, it's basically very simple. You just need to do this method call, and as a parameter, you are going to specify which layout do you wish to be using. And as you can see in this example right here, we are specifying that we want to be using C layout. So when we do that, we know that inside of this block of code that follows this instruction, we will be using the memory layout exactly the same way as C and C++ compilers do. And of course, there are quite a few more memory layouts out there. And this one is just an example because I want you to be aware of this problem and know how to tackle it when you run into it in real life. And that's basically the whole point of this. That was quite a tough video, I have to say. We managed to cover some very advanced and complex topics, so I hope that I did a fairly good job at least to simplify all the concepts that are being used here so that we could actually understand what is going on when we work with values and we try to store them in memory. And if I did, it would really mean a lot if you could please like this video and subscribe to the channel, because it would definitely help out both of us to grow and to spread the word about Rust and all of its features. And in our next video, ladies and gentlemen, we will be starting our discussion about functions. And you should be aware of the fact that that video is probably going to be the most important video so far. So you make sure to be there when it releases. And there is basically only one thing left, and that is for me to wish you an amazing day. Until the next video, goodbye.